Now that we know how to draw formal charge, let's see how we can use formal charge and when we're drawing our resonance structures. So, the molecule on the left here, I have a negative formal charge on this oxygen. So if you don't understand formal charge, go back and watch the previous videos here. So there's a negative formal charge on this oxygen. And it turns out this one dot structure is enough to describe what's actually happening in this molecule. The negative charge is localized to this oxygen atom. So, this is good enough, but sometimes you have situations where one dot structure is not good enough to completely describe what's happening in a molecule, and that would be our second example here. So in our second example, we have a negative formal charge on our oxygen atom, like the first example, but in this case, it turns out that this negative charge is actually spread out throughout this molecule. It's actually delocalized, and some of that negative charge is actually going to be shared by the top oxygen. So somehow we have to draw another dot structure for this molecule showing electrons somehow getting up here to this top oxygen, and that will be a resonance structure. So what could we do to show the movement of electrons from the bottom oxygen to the top oxygen? Well, I could say, oh, well, these two electrons in blue here, right, I could show those two electrons moving. So what if they moved in here to form another bond between my carbon and my oxygen atom? So let's draw what that would look like, right? So I had my bonds like this, and then I had one bond from this oxygen, and then this top oxygen here had its lone pairs, and then I showed the movement of two electrons. Remember, one bond is equal to two electrons. So I showed the movement of two electrons into here to form a new bond between that carbon and that oxygen. So I might think this would be a resonance structure, but it is not a resonance structure, and the reason why is because of the number of electrons that surround this carbon atom right here. There are 5 bonds to that carbon, and since each bond consists of 2 electrons, that would be 10 electrons around that carbon, which is more than 8, right? It would violate the octet rule. Carbon being in the second period of the periodic table, carbon can never have more than 8 electrons around it. It can never have 5 bonds to it because it has only 4 orbitals in the second period. So this is not a resonance structure, right? So this does not work. So whenever you're drawing resonance structures in the future, remember you cannot violate the octet rule. So let's see, what can we do? What can we do to move those electrons up to my top oxygen? So I'll start with that same picture there, and let me go ahead and put in those electrons in blue like I did before, and I'm actually going to make a pi bond in here magenta, right? So there's my pi bond in that molecule. So I'm going to start off the same way. I'm going to say these 2 electrons in here can move in here to form a double bond. But that's too many bonds to that carbon, so something has to give, right? Something else has to change. And the electrons in magenta, the ones in this pi bond here, are going to move out onto my top oxygen. So let's draw what would happen if the electrons move that way. So now I'll go ahead and put in my resonance arrow there. Now I would have my top oxygen. The magenta electrons had moved out onto my top oxygen, so I can show that like that. And on my bottom oxygen, right, 1 lone pair had moved in to form a double bond. That leaves 2 lone pairs behind. And let me go ahead and show what happened to those blue electrons, right? They moved in there to form a new pi bond. So this would be a resonance structure. And whenever you're drawing resonance structures, you must put your formal charges in, right? So over here on the left, our negative charge was on the oxygen. What happened to that -1 formal charge, right? Well, it actually moved to this top oxygen here, right? So real quickly, if I wanted to find the formal charge on this top oxygen, right, we already know how to do that. Let's just prove that I have 7 electrons around it, and it likes to have 6. So 6 minus 7 would give me -1. So the negative formal charge moved to my top oxygen. And so these two are resonance structures of each other. So let me go ahead and put in resonance brackets, right? So these are my resonance structures. The electrons are not confined to the bottom oxygen atom, right? The electrons are actually delocalized throughout the entire molecule. So which one of these two pictures is the best one to think about for our molecule? And in reality, it's neither one. Both of these are pictures of showing the movement of the electrons. But in reality, the electrons are already delocalized throughout all these atoms already. All right. So if we could draw a picture of that, we would say, okay, well, the bonds between oxygen and carbon, right, these bonds are not single bonds, nor are they double bonds, right? They have some character of both, right? They have some character of single bonds and double bonds, so they're like a bond and a half, right? So if I draw like this little picture here, right, you could see it's kind of like a bond and a half. So in reality, right, these are like bonds and a half. So you draw your dashed line like that. And studies have shown that these bonds are the length that you would expect for, like, 1.5 bonds. And we call this the hybrid, right? The resonance hybrid. So this picture is a slightly better picture of what the molecule actually looks like. The molecule is actually a hybrid of my two resonance structures. So it's very tempting to say, oh, the molecule is resonating back and forth between my two resonance structures. But that's actually not true. In reality, the electrons are already delocalized, and this is a better picture of what's actually happening. So the more you're able to delocalize electrons, the more stable the molecule is. So that's a very important point. So if I can delocalize electrons, right? So the more I delocalize electrons, right, the increase in delocalization, the more spread out those negative charges can be, and the more stable the molecule is. So if you increase the delocalization, you increase the stabilization, you make the molecule more stable. So the more resonance structures you can draw, the more stable the molecule will be. So let's point out a few things about my resonance structures, right? Well, first of all, I showed all formal charges. So always show formal charges for resonance structures. If you don't, it's incorrect. You should also show your resonance double-headed arrow here in the center, and then your brackets surrounding your resonance structures. And when you're showing the movement of your electrons, you always use these curved arrows here, right? These curly arrows. So these always point in the direction of the movement of your electrons. So the blue electrons moved in here to form a double bond, right? So that's why we drew our arrow pointing this way. Sometimes students will change the direction of arrows, and don't do that. Always think, what direction are my electrons moving? All right, well, let's look at some patterns. Let's look at some patterns to figure out how we can move some electrons around, right? Well, one thing that you can do to draw a resonance structure is you can look for a lone pair of electrons that you can turn into a pi bond, right? So a lone pair of electrons that you can turn into a pi bond. So we've already done an example of that. So right up here, the blue electrons, right? They started off as a lone pair of my resonance structure on the left, and I moved them in here to form a pi bond, right? So they're a pi bond on my second resonance structure. So what's our second pattern? Our second pattern is the opposite of our first. We could take the electrons in a pi bond, and we could move those to form a lone pair of electrons. So that is what we have done for the electrons in magenta, right? They were a pi bond here, and the electrons in that pi bond, those two electrons moved off onto my top oxygen to form a lone pair of electrons. So that is our second pattern to look for drawing resonance structures. And our third pattern is, well, we could start with the electrons in a pi bond, and we could just turn those electrons in that pi bond into another pi bond. So let's do an example where that occurs. So let's look at an example where electrons from one pi bond can form a new pi bond. So here I'm just going ahead and drawing a carbon skeleton with some hydrogens on my carbon, like that. And I'm going to represent my pi bond electrons in blue. So there's my pi bond there. So I have a carbon double bonded to another carbon. Where are my formal charges, right? Well, if you could take the time to calculate the formal charge in all of these atoms, and you will find out that this carbon is positively charged, right? Because it has only 3 bonds around it. So this is my carbocation. What can I do to spread out or delocalize that positive charge throughout my entire molecule? I could go with my third pattern here, right? I could move electrons from one pi bond to form another pi bond. So what would happen if I moved electrons from this pi bond over here to form another pi bond? Well, let's go ahead and draw our resonance brackets and our resonance arrow here like that. Now, what would happen? Well, my carbon skeleton stays the same, so we're not going to mess with single or sigma bonds when we're doing our resonance structures, only pi bonds. So what would happen if I move that pi bond over here to this carbon, right? Well, I could go ahead and draw, right? Those electrons had moved over here to form a double bond right there. Where did my formal charge go, right? Because if I look at this carbon, it now has 4 bonds around it, so it's perfectly satisfied. So our formal charge had to move somewhere, and it moved to this carbon, right? Now this carbon is the one with only 3 bonds around it, so it gets a +1 formal charge. So we've been able to delocalize our positive formal charge by showing the movement of electrons in one pi bond to form another pi bond. Right, so if I were to draw these two resonance structures again without drawing my hydrogens, right, so we go ahead and show this whole thing again without drawing the hydrogens, it looks a little bit more complicated, but this is the exact same thing, right? So these electrons are going to move over here to form a new pi bond, and then my molecule would look like this. And my formal charge moved to this carbon, right? So sometimes when you take the hydrogens away, students will get confused because they're not sure where that positive charge goes. So if you need to, go ahead and draw on your hydrogens, and then obviously it's very easy to assign formal charge then. Let's do one more example. I had a movement of one pi bond. Let's do one where I have several double bonds in my molecule. Let's do 2 double bonds, so something like this. So I start out with a molecule with 2 double bonds, and I'm going to say this is my formal charge. So how can I draw a resonance structure for this molecule? Well, I'm first going to show the movement of these pi electrons over here, and what would that do, right? That would actually take away a bond from this carbon, right? So let's see what I would get. So let me go ahead and put in my carbon skeleton there. Well, I moved some pi electrons over here to form a new pi bond, and I took away, right? I took away a bond to this carbon, right? This carbon lost a bond, so that is where my new formal charge is going to go, right? So my formal charge is on this carbon right now, and the other double bond is still there like that. So I can draw one more resonance structure, right? I can spread out or delocalize that positive charge even more, and that's because I could show now the movement of these pi electrons over here. And so I'm adding a bond to this carbon now, so that positive charge is going to go away, and I'm taking away a bond from this carbon. So let's go ahead and draw the carbon skeleton for the next resonance structure, right? So I had my pi bond over here. I'm forming a pi bond right here, and I'm taking away a bond to this carbon. So my positive formal charge, my carbocation, will move over here to this carbon. So I was able to draw 3 resonance structures to help to stabilize this molecule.